Have you ever stopped and really thought about the ultimate mystery of neuroscience? I mean, how exactly does wet, squishy brain matter, essentially a 3-pound lump of biological tissue inside your skull, somehow generate the vivid, continuous, high-definition movie of your subjective experience? How do completely physical atoms and molecules give rise to the actual feeling of being alive, of seeing a vibrant color, or feeling joy? It's a massive question, and it's one that has totally baffled scientists and philosophers for centuries.
Well, welcome to This Explainer. Today, we're diving into one of the most fascinating, mind-bending, and fiercely debated frameworks out there, attempting to decode this exact mystery. It's called Integrated Information Theory, or IIT for short. Proposed back in 2004 by neuroscience Giulio Tononi, IIT doesn't just try to find where consciousness happens in the brain. It actually attempts to explain what consciousness is at a fundamental mathematical level.
Part 1. Flipping the script. To really wrap our heads around IIT, we first have to understand how it completely flips traditional science on its head. Normally, we start with physical evidence, right? We look at brain scans, we observe neurons firing, and then we try to figure out how those physical actions magically squeeze out a conscious thought. But IIT? It takes the exact opposite path. It uses a deductive, experience-first approach. It works backwards. It starts by identifying self-evident truths about human experience. Things that are just undeniably true about what it feels like to be conscious. And from there, it actually deduces the mathematical and physical properties a system absolutely must possess to create that experience.
So IIT identifies these 5 core axioms as the absolute rock-solid foundation of the theory. You have intrinsic existence, meaning your experience exists for you, from your own perspective. Then composition, your experience is made of multiple structured components, like seeing a green field and a soccer ball at the same time. Third is information. Every specific experience is highly differentiated from any other possible experience. Fourth is integration. Your experience is unified. You literally can't split your visual field down the middle. And finally, exclusion. Your experience flows at a specific speed and contains definite content. No more, no less.
Part 2. Information and integration.
Out of all those axioms we just ran through, information and integration really act as the mechanical heart of this entire theory. Think about what happens when you look at a simple object, like a cue ball on a pool table. Your experience is highly informative because it's specifically a cue ball, right? Not a blue cube of pool chalk. But crucially, it's completely integrated. Your brain inextricably fuses its spherical shape and its white color together. You cannot unexperience the whiteness from the roundness. They are permanently bound into a single unified conscious state.
And this actually brilliantly illustrates the mechanics of the theory when we contrast it with a machine. Let's compare the isolated photodiodes of a digital camera capturing a photo of that exact same cue ball with the highly interconnected, glowing neural pathways of a human visual cortex looking at it. Both systems are processing data, sure, but they are doing it in fundamentally different ways.
See, a digital camera captures a massive amount of data, but its sensors are entirely isolated from one another. The pixel in the top left corner has absolutely zero interaction with the pixel in the bottom right. This generates what's known as Shannon information. It's an image that is highly meaningful to an outside observer, like you or me looking at the photo on a screen, but it means absolutely nothing to the camera itself, because the camera doesn't integrate the data internally.
Now your brain, on the other hand, relies on intricate looping reentrant feedback connections. It generates what IIT calls intrinsic information. The interconnected parts of your brain are making a direct causal difference to one another. The system isn't just spitting out information for an outsider to look at, it's making a difference to itself. And under this theory, that physical cause and effect power upon itself is the baseline physical requirement for consciousness. Part 3. Measuring consciousness with phi. Because IIT roots our subjective experience in these objective physical dynamics, specifically parts interacting and causing effects on each other, it arrives at a pretty wild conclusion. We can theoretically measure exactly how much consciousness a system has. Enter phi, represented by the Greek letter. In the mathematical framework of IIT, phi is the metric used to quantify a system's maximum integrated information. The theory argues that this number is a direct, quantifiable measure of a system's consciousness. If a system has a phi greater than 0, boom, it possesses some degree of consciousness.
So let's jump back to our digital camera. Because its sensors don't interact, they don't affect each other, and they definitely don't integrate information, the math is incredibly simple. Its phi value is exactly 0. It experiences nothing. A camera is basically just a feed-forward tube of isolated data. But take a densely interconnected system, like the human cerebral cortex with its billions of neurons and trillions of synapses constantly firing back and forth. That would possess a massively complex, sky-high phi value. And under IIT, that incredibly high number equates to the rich, highly differentiated, and profoundly unified conscious experience that you and I are enjoying right now.
Which brings us to IIT's absolute boldest claim. It's called the explanatory identity. IIT does not say that consciousness just sort of magically arises or emanates like a vapor from this integrated information. It claims that consciousness is mathematically and physically identical to this irreducible cause and effect structure. The specific geometry of that network inside the brain is literally what dictates why the color red feels like red and a musical note sounds like a musical note.
Part 4. A highly debated proposal.
As you can probably guess, reducing the grand mystical mystery of the mind to mathematical structures has ruffled more than a few feathers. It has ignited an intense, ongoing debate within the scientific community. On one side, you have renowned neuroscientists like Christoph Koch, who strongly praise IIT, and these proponents point to the theory's remarkable ability to make testable clinical predictions. For example, IIT principles actually help develop tools like the Perturbational Complexity Index. This tracks brain responses to magnetic pulses to accurately detect hidden consciousness in brain-injured patients, or to measure differences in brain integration during sleep, anesthesia, and even epileptic seizures. It's real, practical stuff.
Yet there is a fierce backlash. This really blew up in a highly publicized 2023 letter signed by 124 scholars who sharply criticized the theory's deductive foundations. Because calculating exact phi values for large brains is currently impossible, these critics argue the theory can't be fully falsified right now. They went so far as to label it a pseudoscience until more empirical testing can actually validate its core mathematical claims.
Let's break down those criticisms neutrally, because a few key arguments emerge. First, calculating phi for an entire human brain isn't just hard, it is computationally intractable with our current technology. Second, critics argue that IIT's deductive approach relies way too heavily on theory before gathering real-world empirical evidence. And finally, because IIT says literally any system with interacting parts has a phi greater than 0, the math technically implies that a simple artificial sensor, like a basic photodiode, might possess a tiny, fundamental sliver of consciousness. That's a form of panpsychism that a lot of traditional scientists flat out reject. Opponents also leverage what's known as the unfolding argument. This is a mathematical proof showing that purely feed-forward neural networks, the ones that lack those looping connections and therefore have a phi of 0, can actually be trained to compute the exact same inputs and outputs as highly conscious recurrent networks. Critics argue this is a major problem for IIT. If two circuits behave identically, but only one is conscious according to the math, how can we ever empirically test which structure is truly present?
However, defenders of IIT counter this by pointing straight back to biology and evolution. They argue that, sure, the unfolding argument works in a clean computer simulation, but a massive feed-forward system capable of mimicking a human brain in reality would be unbelievably bloated, energy-expensive, and biologically inefficient. Darwinian natural selection would just never allow it to evolve. Evolution naturally selects for the compact efficiency of highly integrated, recurrent systems. So they argue this beautifully bridges IIT's mathematical requirements with harsh biological reality.
Ultimately, whether you view it as a profound scientific breakthrough or just a flawed model, IT undeniably remains a highly debated proposal rather than an absolutely established fact. But what it does do, for sure, is provide a profoundly rigorous framework. It finally gives researchers a specific mathematical language to test, challenge, and debate the physical substrates of our inner world. Which leaves us staring at this elegant, almost cosmic puzzle. It totally reframes how we look at the brain, biology, and perhaps the universe at large. And it forces us to ask one final, profound question to carry with us today. Could consciousness, the very essence of our subjective existence, actually be understood as a fundamental physical property of integrated information itself?